Hello everyone, welcome to the second lesson on optimization. Question: an island is 2 miles due north of its closest point along a straight shoreline. A visitor is staying at a cabin on the shore that is 6 miles west of that point. The visitor is planning to go from the cabin to the island. Suppose the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? So let us draw a picture of this situation. Here we have our island out somewhere in the sea. Here is our shoreline. The direct distance from the island to the shoreline is 2 miles. Here is our cabin, which is 6 miles from the point on the shore where our measurement from our island is. So if we let the distance from the cabin to the point on the shore where our visitor will run to before he swims be x, then the distance from there to the point on the shoreline measured from the island directly was 6 minus x. And we can assign another variable y to the distance that the visitor will swim. Now, we want to find the time, right? Let the time t, let's say uppercase T, be the total time taken to travel from the cabin to the island. Then, this time will consist of two separate parts. A time taken to run, let's call that T sub r, and a time taken to swim, let's call that T sub s. Now, T, it's uppercase T, will be equal to TR, or T sub r, plus T sub s. We want to minimize T. We know that our running rate was 8 miles per hour and the swimming rate was 3 miles per hour. Also, the distance is equal to rate times time. So time will be equal to distance over rate. So let us put that in the context of what we know then. T sub r will be equal to x over 8 and T sub s will be equal to y over 3. So therefore, T will be equal to x over 8 plus y over 3. But we want to express T just in terms of one variable. So then we want to, let us say, express it in terms of variable x, which is our variable of choice here. And so let us use our Pythagorean theorem with 2, 6 minus x, and y on our hypotenuse. So y squared will be equal to 2 squared plus 6 minus x all squared. So y will be equal to the positive square root of 4 plus parentheses 6 minus x all squared. It should be all squared, right? Now, we have y in terms of x, so we can replace our y, therefore, with what we have here in terms of x. Therefore, our uppercase T will be equal to x over 8 plus radical 4 plus 6 minus x all squared over 3. We want to think of the possible domain for x values. We want x to be positive. We want to be greater than or equal to 0. And of course, x will be less than or equal to 6 because 6 miles is the maximum that he can run on the shore, or the visitor can run on the shore. T is a continuous function on the interval. I'm going to take derivatives and set it equal to 0, or to minimize this, so t prime of x, same as dx dt, by the way, no, dt dx, sorry, be equal to 1 over 8 plus, taking the derivative, 1/2, 4 plus 6 minus x all squared raised to the negative 1/2 over 3. And then by the chain rule, that will be times 2, parentheses 6 minus x by -1. And let's simplify this a little bit and then set it equal to 0 and solve for x. 1 over 8 minus 6 minus x all over 3 times parentheses 4 6 minus x all squared raised to the 1/2. We can still do a little bit better. That's going to be 1/8 minus 6 minus x all over 3 times radical 4 plus parentheses 6 minus x squared. I want to set this equal to 0 and try to solve for x. It's a bit of a algebra to do right here, but let's do it. Set it equal to 0. Then say bring in the 1/8 over and multiplying through by -1, or just bring in the 6 minus x over radical 3 radical 4 plus 6 minus x all squared. It will give you the same result. And then by just multiplying both sides by 8 and then by 3 times radical 4 plus 6 minus x all squared, we end up with 8 times 6 minus x, or some people might just say cross multiplying. Whatever method you prefer to call it, we'll end up with the same thing, whether we do it in 2 or 3 steps or whatever. 8 times 6 minus x is equal to 3 times radical 4 6 minus x all squared, and continue to solve that square on both sides and so on and so forth. We will end up eventually with x is equal to 6 plus or minus radical 36 over 55. And then we can simplify that a little bit more to x will be equal to 6 plus or minus 6 over radical 55. And then the 6 plus 6 over radical 55 will give you 6.089. And it says this is not in the domain because x cannot be greater than 6. But 6 minus 6 over radical 55 will give you 5.19, and that is in the domain. So therefore, that is the one that we're looking for. So then t will be equal to, or the t of 6 minus 6 over radical 55, and that will give us 1.368. That is this equation, the t of 5.19. That will give us the time. We could test the endpoints as well, the t of 0 and the t of 6. T of 0 will give you 2.108. T of 6 will give you 1.417. So the t of 6 minus 6 over radical 55 is our local minimum because it's the lowest value in that interval. The owners of a car rental company have determined that if they charge customers P dollars per day to rent a car where 50 is less than or equal to P less than or equal to 200, the number of cars they rent per day can be modeled by the function N of P is equal to 1000 minus 5P. If they charge $50 per day or less, they will rent all their cars. If they charge $200 per day or more, they will not rent any cars. Assuming the owners plan to charge customers between $50 per day and $200 per day to rent a car, how much should they charge to maximize their revenue? Out here for this problem, a diagram is not needed, so I just drew a little box car right here. Variables: P is the rental price of cars, N is the number of cars, R is your revenue. The equation is R is equal to N times P. And the number of cars rented, the equation for that, N of P is equal to 1000 minus 5P. R of P is equal to N times P. That's going to be 1000 minus 5P times P. And so that's going to be equal to 1000P minus 5P squared. The effective domain, P will be equal to 50 to P equals $200. So we're given the effective domain. We want to maximize R in the interval of 50 to 200. And so we know r is continuous on this interval because, of course, the quadratic function, it's polynomial, polynomials continuous. So I want to find r prime and set it equal to 0. So r prime of p is equal to 1000 minus 10p. Setting that equal to 0 and solving for p, 10p is equal to 1000. So p is equal to 100. That is our critical point. Then I want to find r of p at 100, r 100. Plug that into a revenue function. It's going to be 1000 times 100 minus 50 times 100 squared. That's going to be equal to 50,000. That's our maximum. If you want to check the endpoints, we can. So let's do r of 50 and we end up with 37,500. And r of 200, that is 0. So that ensures, after we check the endpoints, that 50,000 is our maximum that we can get. Let's look at another question. A rectangle is to be inscribed in the ellipse x squared over 4 plus y squared is equal to 1. What will be the dimensions of the rectangle to maximize its area? And then what is the maximum area? Sketch a diagram. We can use the graphing tool for this. Here I've just made a rough sketch. This is our ellipse. X squared over 4 plus y squared is equal to 1. And this is a point x, y on that ellipse where our rectangle sits inside the ellipse, and where a point or a corner of the rectangle or vertex or rectangle touches the ellipse. We want to maximize the area of the rectangle. Let A be the area of the rectangle, in L the length of the rectangle. This is the length of the rectangle, and W is the width of the rectangle. Width of the rectangle. L will be equal to 2x, and W is equal to 2y. Okay, so the equation A is equal to L times W. That's going to be 2x times 2y. Since x squared plus y squared is equal to 1, we can get y squared is equal to 1 minus x squared over 4. And we want to plug that back into our area equation at some point. So, but we want to find y by itself. Y would be equal to radical 1 minus x squared over 4. And keep on simplifying that. Radical 4 minus x squared over 4 would be radical 4 minus x squared over radical 4, which should be radical 4 minus x squared over 2. So we plug that back into our area function, replacing y with radical 4 minus x squared over 2. So A will be equal to 2x, parentheses 2, radical 4 minus x squared over 2, and that would be 2x, radical 4 minus x squared. So our domain here, we want x to be greater than 0 to x is less than 2. I want to find that derivative and then set it equal to 0 to find the maximum. A prime of x, and the derivative, that's going to be 2x dx, radical of 4, 2x ddx of 4, radical 4 minus x squared, plus radical 4 minus x squared ddx of 2x. We're using our product rule there, and so that's going to be equal to negative 2x squared over radical 4 minus x squared, plus 2 times radical 4 minus x squared, and then keep on simplifying that. That becomes 8 minus 4x squared over radical 4 minus x squared, and setting that equal to 0 and solving for x. We have x equal to plus or minus radical 2. X cannot be negative radical 2 because that is not in our domain because it's a negative number. So x equal plus radical 2 is the possible solution there. And then if x is equal to radical 2, y will be equal to square root of 1 minus radical 2 squared over 4. And that will continue simplifying that. That becomes 1 over radical 2. So the dimensions of the rectangle would be L would be equal to 2x, that's going to become 2 radical 2, and W is equal to 2y, that's going to be 2 times 1 over radical 2, and that would be equal to radical 2. And so those are your dimensions of your rectangle. And to find the area of the rectangle, we multiply these two together, 2 radical 2 times radical 2.